we looked at NMR states. So in summary, we were able to draw a block sphere and we were able to identify quantum states psi, which are spin states, and these spin states, these vectors live on different points on the block sphere. And we identified the north pole as being the state alpha, the south pole as being the state beta, the x point being the state alpha plus beta under root 2. This point was identified as alpha plus iota beta under root 2. The point at the far end was alpha minus beta over under root 2. This point was alpha minus iota under root beta over under root 2. At any arbitrary point on the surface of this sphere, any arbitrary point on the surface of this sphere could be represented as cosine theta over 2 alpha plus e I phi sine theta over 2 beta, where this is the angle phi and theta is the angle of the co-latitude. So the quantum spin, such as the proton spin, could be represented by this state vector, and this state vector was found to lie on a block sphere. Okay. So this is one way of representing states. What is the other way of representing a state? Bilal? So we can write a Hermitian matrix for the state, and that matrix is called the density matrix. So exactly on the same block sphere, we were able to make another identification, and that identification was that this point is Ix, this point is Iy, this point is Iz, this point is minus Iz, correct? Now suppose we draw another point along the equator, and this angle is phi. Okay. So this point will also represent a certain quantum state, and that quantum state will be Ix cosine phi plus Iy sine phi. What about this point, which corresponds to the state cosine theta over 2 alpha plus ei phi sine theta over 2 beta? This point is the analogous point on the block sphere. This should also be representable by a certain density matrix, and that density matrix is given by Ix cosine phi plus Iy sine phi sine of theta plus Iz cosine of theta. Where this angle is theta. So if you take this point, if you take this quantum vector, this state vector, and find the corresponding density matrix, simply by doing this operation, you will find the density matrix of this point to be represented by this operator. So both of these are equivalent representations of a state. ठीक है? अब एक फर्क थोड़ा सा आप देख रहे हैं कि यहाँ पे कोसाइन थीटा ओवर 2 है, साइन थीटा ओवर 2 है, लेकिन यहाँ पर कोसाइन फाई है, साइन फाई है और साइन थीटा है, थीटा ओवर 2 नहीं है और ये कोसाइन थीटा है. ठीक है? If you do the algebra, find the outer product, this is the state that you will get. Here you are noticing that these coefficients can be complex. This can be a complex number. This is a complex number if phi is not equal to 0. But here the coefficients are real. Cosine phi, sine theta, cosine phi. So any point on the block sphere can also be represented by a vector, a block vector, which has components cosine phi sine theta, sine phi sine theta, and cosine theta. ठीक है, ये एक वेक्टर है ना जिसके बेसिस ऑपरेटर IX है, IY है और IZ है, और जो प्रोजेक्शंस है along IX वो कोसाइन फाई साइन थीटा, साइन फाई साइन थीटा और कोसाइन थीटा. So both of these are equivalent representations of a state. So what is the advantage of this approach over this approach? ये भी स्टेट को रिप्रेजेंट कर रहे हैं, ये ऑपरेटर्स. एक फर्क ये है कि ये ऑपरेटर दरअसल मैट्रिसेस है, ठीक है, ये वेक्टर्स है. ये वेक्टर्स थे, हमने उस वेक्टर के कॉरस्पॉन्डिंग एक मैट्रिक्स लिख लिया. लेकिन देयर इज अ सर्टेन एडवांटेज ऑफ दिस अप्रोच. व्हाट इज द एडवांटेज?
एक तो सिंपल रिप्रेजेंटेशन,
सिंपलर तो नहीं है, कुछ रिस्पेक्ट्स में कॉम्प्लिकेटेड है. मैट्रिक्स इज ज्यादा कॉम्प्लिकेटेड है, ज्यादा एलिमेंट्स हैं मैट्रिक्स के अंदर वेक्टर स्कीम्स में. आपका नाम है ज़ैन.
I would guess multiple system again हम अगर 2x2 system या larger system में जाएंगे तो matrix जो solution है that would be more preferable. हम यहाँ पे सिर्फ एक उसके साथ डील कर रहे हैं, एक इलेक्ट्रॉन के साथ प्रोटॉन. सॉरी,
देखो फर्क एडवांटेज इस अप्रोच का ये है, you can deal with pure states as well as mixed states. Here you can only deal with pure quantum states. If you have n spins and half of them are in a particular state and half of them are in a particular state, it's more convenient to write a density matrix rather than the quantum state. So this approach works for mixed states as well as pure states. ठीक है? अच्छा, तो ये हमने पिछली दफा ये चीज देखी थी. अब आप ये देखें कि हमने पिछली दफा ये भी देखा था कि in an NMR experiment which starts off at a certain temperature, the initial state is very important, and that initial state is given by the equilibrium density matrix, and that is simply identity over 2 plus some factor epsilon IZ. So every NMR experiment starts in this state. Now this epsilon is h bar omega over 4 kBt when kBt is much larger than h bar omega in the high temperature approximation. So this is a very small number. This is an extremely small number, which means that if you have a test tube which contains water, the population difference between spins in one state versus the spins in the orthogonal state is very small. So the polarization in NMR is extremely small. That's why NMR is an extremely insensitive technique. And the only way which makes NMR possible is the sheer number of spins, is the volume of the sample.
can you repeat that?
Now this is a very small factor. Okay? Now suppose this factor were 0, then the density matrix would simply have been identity over 2, which means that half the spins would be in one state, in the alpha state, and half of them would be in the orthogonal state, in the beta state, which means that if you were to draw two energy levels, both of these levels would be equally populated if you were to make a simplistic picture. But now what is happening? There is a slight excess of spins in the lower energy level. slight excess of spins in the lower energy level, and that is slight because this number is very small. And this population difference is what gives rise to the NMR signal. And how can you increase this signal, increase this polarization? This represents polarization, if you are with me on this. This represents polarization. How much signal can you get from the NMR sample? Now this polarization can be increased by increasing omega. That is by increasing the energy spacing between the two levels. That is by increasing the magnetic field, for example, or decreasing the temperature. But as we've seen, there are limitations to that. So this is where we ended our discussion the other day. Now we will proceed from here. And today we will look at NMR operations. We've talked a little bit about states. Now how does an NMR experiment take place? What is an NMR experiment? And how do we acquire signal from a test tube of water? Okay, so this is the goal of today's lecture. And from the next lecture we look at the NMR spectrum of different organic compounds. Okay, but it's very important to build up these principles. ठीक है, यहाँ तक कोई क्वेश्चन पूछना है?
So next of your contributions to that. So which one is blocks verification? We can write as many states as we want. कोई भी स्पेस में लाइव कर सकते हैं. Then we can write this state for it. वो it can be mixed in that case.
Sorry,
So multiple points पे हम उसे present कर सकते हैं. तो वो that would find a mixed subblock, a mixed state define. Like अगर हम दो different points पे अगर
ठीक है, एक स्टेट यहाँ अल्फा पे लाई करेंगे, एक स्टेट यहाँ बीटा पे.
तो वो मिक्स नहीं है. तो लेकिन वो प्योर तो नहीं है. It has two states.
नहीं, फिर आपको हर एक ब्लॉक स्फीयर में बहुत से वेक्टर्स बनाने पड़ते हैं. एक ब्लॉक स्फीयर में बहुत से वेक्टर्स बनाने पड़ते हैं. अब बिलफर्ज आपके पास 1000 स्पिन है. ठीक है, आप 1000 वेक्टर्स बनाएंगे कि नहीं? अब एक पॉइंट, आप पूरी क्वांटम मैकेनिक्स डेंसिटी मैट्रिक्स जो है ना, वो सारी की सारी इंफॉर्मेशन आपके अंदर चलो यार, बहुत शुक्रिया. अब जो डेंसिटी मैट्रिक्स के अंदर सारी की सारी इंफॉर्मेशन मौजूद है, उससे आपने क्या सिग्नल लेना है, पोलराइजेशन कितनी है, ठीक है. और डेंसिटी मैट्रिक्स इस ब्लॉक के ऊपर एक पॉइंट है. ठीक है, हाँ ये मुमकिन है आपके पास मिक्स स्टेट है तो आप इस पूरी ब्लॉक स्फीयर को स्पटर कर दें पॉइंट्स के साथ. दैट इज लाइक मेकिंग 1000 different block spheres. Every sphere has its own block sphere. But you can write one density matrix and represent it by a single point on the block sphere. ठीक है? तो ये बात आपको समझ आ गई कि this corresponds to a polarization. ठीक है? तो ये बात हमने NMR states के मुतालिक कर ली कि स्पिन की क्वांटम मैकेनिकल स्टेट क्या है जब NMR एक्सपेरिमेंट शुरू होगा. अब हम देखते हैं हाउ डज एन NMR एक्सपेरिमेंट प्रोसीड विद टाइम. हाउ डज एन NMR एक्सपेरिमेंट लुक लाइक, हाउ डज इट मॉडिफाई द स्टेट्स, एंड हाउ डू वी फाइंड द सिग्नल दैट वी कैन मेजर फ्रॉम एन NMR experiment. Now suppose, let's start with something that is very simple. If you have a quantum state psi, now we're talking about this vectorial picture. ठीक है, एक वेक्टोरियल पिक्चर है, एक डेंसिटी मैट्रिक्स पिक्चर है, दोनों स्टेट्स को रिप्रेजेंट कर रहे हैं. If you have a vector, a state vector psi, then we know that the Schrödinger equation is given by this Hamiltonian psi. ठीक है, ये आपने पढ़ा होगा ना क्वांटम केमिस्ट्री. ओके. Now the solution of this Schrödinger equation is psi as a function of time is psi as a function at time t equals 0, exponent minus iota Hamiltonian time over h bar. So this is a solution of the Schrödinger equation. That is, you start off with the quantum state psi naught. There is some Hamiltonian, and you allow that Hamiltonian to act for a time t, and you end up in the state psi as a function of t, which is given by this expression. Alright. Now suppose you are performing an experiment. You are performing an experiment in which the initial state at time t equals 0 is alpha plus beta under root 2. That is, if you draw the block sphere, you are here initially at time t equals 0. Okay, you along the x-axis. Now you have a Hamiltonian. Somehow the spins start off in this state, so it's a non-equilibrium state. If you were in equilibrium, you would be lying here on the block sphere along IZ. But suppose you start off with a state which is not in equilibrium, but is a superposition of alpha and beta. And now you place your test tube inside a magnetic field which points along the z direction. This is your magnetic field. So constant with time. ठीक है? हमने z axis के along field apply किया. So there is a Hamiltonian corresponding to this situation. अब एक field apply की उसका एक Hamiltonian होगा. वो Hamiltonian आपको पता है क्या होगा? वो Hamiltonian होगा ओमेगा नॉट IZ. अच्छा, अब ये मैं कैसे याद रखूं ये Hamiltonian ये है. ठीक है? अच्छा, Hamiltonian क्या है? इसको मोटिवेट करने के लिए कि हैमिल्टोनियन यही है, इसको मोटिवेट करना बहुत आसान है. देखिए, आपके पास दो एनर्जी लेवल्स बन रहे हैं जब एक मैग्नेटिक फील्ड z एक्सिस के लॉन्ग अप्लाई किया. एक एनर्जी लेवल है बीटा, एक एनर्जी लेवल है अल्फा, और इन दोनों के दरमियान एक एनर्जी स्पेसिंग है डेल्टा ई. ठीक है, which is given by h bar omega naught. Omega naught we know is the Lahore frequency, and this is also equal to minus h bar gamma b naught. We know this from lecture number 1. Okay? So if we measure the energy in this state, the energy in this state E beta is given by minus h bar omega naught over 2, and the energy in this state E alpha is given by h bar plus h bar omega naught over 2. ठीक है? Agreed? So this is something that we know from lecture number 1. So what is the Hamiltonian operator? The Hamiltonian operator is such an operator which, when acts on a state psi, gives you the energy of the system which exists in that state. So this is the definition of the Hamiltonian. Agree? Provided the Hamiltonian does not change with time and the wave function does not change with time. This is the time independent Schrödinger equation. So now we have a Hamiltonian which, when acts on the state beta, returns a certain energy minus h bar omega naught over 2 beta, and which the same operator, when acts on the state alpha, returns plus h bar omega naught over 2 alpha. ठीक है? So if we were to write the Hamiltonian in matrix form, we define a basis. We define the basis that alpha is represented as 1 0 and beta is represented as 0 1. Now if we define a Hamiltonian matrix in this particular basis as h bar omega naught over 2 1 0 0 minus 1, then the whole picture knits in together. That is, this Hamiltonian, when acting on the state alpha, when acting on this state, will give you plus h bar omega naught over 2, and this Hamiltonian, when acting on the state beta, will give you minus h bar omega naught over 2. And what is this Hamiltonian? This Hamiltonian is h bar omega naught Iz. Oh, sorry, omega naught Iz. If I can define h bar to be included inside this Pauli matrix as well. Okay? Different authors use different convention, but let's stick to this convention. Okay? So the Hamiltonian is given by some frequency, some Lama frequency, which is the spacing between these energy levels, and an operator Iz. Iz because the field is along the z direction. If the field were along the x direction, we would have omega naught Ix. If the field were along the y direction, we would have a Hamiltonian omega naught Iy. So now we have defined the Hamiltonian. This is our state. In this basis, this is a diagonal matrix, correct? This is a diagonal matrix. अच्छा, अब देखो हमारी ये initial state है, और हमने solution find करना है. How does the state change with time? How does the state change with time? In order to do that, we simply plug in the values. The state as a function of time is given by exponent minus iota the Hamiltonian, which is omega naught Tiz over h bar acting on alpha plus beta under root 2.
सर वो h over 2 दिया omega naught के साथ, वो आपने कन्वर्ट कर दिया Iz,
क्योंकि Iz की डिफाइन हमने किया, Iz की डेफिनेशन के अंदर 1/2 है.
1/2 तो है इंगेज करते हैं.
H का को भी मैंने इसके अंदर डिफाइन कर दिया Iz के अंदर. So Iz is now defined as H पर 2. H को 1 भी ले सकते हैं, हाँ वो मैं बाद में भी. ठीक है? So this is how the state changes with time. Now we have to compute this expression. Let's compute this expression. This is simple linear algebra so far and basic quantum mechanics. As a function of time, our spin state 1/√2 को पहले लिख देते हैं हम, exponent minus iota h bar omega naught T Iz over h bar acting on alpha. Quantum mechanics is linear, इसलिए हम ये कर सकते हैं, minus iota omega naught T Iz acting on h bar acting on beta. So we know that when Iz acts on alpha, the answer should be h bar 2 over alpha. देखो ये Iz acts on alpha, the answer should be h bar over 2 into alpha. And when Iz acts on beta, the answer is minus h bar 2 over beta. Okay? We agree on this. So what we don't have Iz acting on alpha, we have exponent of something Iz acting on alpha. Do you know how to calculate the exponent of a matrix? You know that. Okay? If the matrix itself is diagonal, the exponent of a diagonal matrix is the diagonal of the exponents. So this expression becomes exponent minus iota omega naught t over h bar over 2 alpha. Okay. Plus iota omega naught over so ये h bars cancel out. Okay. So we can, the h bars always cancel out. So we can make our lives easier by not writing h bar because they always cancel out. ठीक है? यहाँ तक समझ आ रहा है ना? मैंने कुछ स्टेप्स में थोड़ा सा तेज चलने की कोशिश कर रहा हूँ क्योंकि हम इस वक्त हमारी जो ज़हनी शऊर है 3rd ईयर पे है और थोड़ा सा ये चीज़ें बार बार देख चुके हैं. अच्छा, 1/2 एक्सपोनेंट माइनस आयोटा ओमेगा नॉट t over 2 अल्फा प्लस एक्सपोनेंट iota omega naught t over 2 beta. So this is the state at any subsequent time. You started off from this point, now time is increasing and this is the new state. This is our new state. Now suppose we put in omega naught t equals pi by 2. ठीक है? Let's choose a time. Omega naught is fixed. ठीक है? Omega naught is given by the gyromagnetic ratio and the magnetic field. Omega naught is the Lahore frequency fixed by the field. Now we somehow put our spins in this state, place them inside a magnetic field and wait. ठीक है? अब हम इंतजार की घड़ियां ये लेंगे. Omega naught t equal to pi by 2 का मतलब ये है कि we wait for a time such that this condition is satisfied. We wait for a time such that this condition is satisfied. Then psi at this time becomes equal to 1/√2. देखो यहाँ pi over 2 आ जाएगा ना, तो pi over 4 आ जाएगा. iota pi over 4 alpha plus exponent iota pi over 4 beta. ठीक है? ये क्या है? एक्सपोनेंट माइनस आयोटा कोसाइन पाई बाय 4 माइनस आयोटा 1 over √2 minus iota over √2. ठीक है? So we have waited for this much time. Now when we wait for this much time, now let's go back here. So our state psi when we have waited for pi over 2 omega naught is given by 1 over under root 2 को मैं कॉमन लेके 1 over 2 आ जाएगा यहाँ पे 1 over 2 1 minus iota alpha plus 1 plus iota beta. Correct? Correct? If I take 1 minus iota as common, I get alpha Is this correct? ठीक है? Alright. अब एक ये वाली टर्म देखें, इसके साथ कोई प्री फैक्टर आ रहा है जो इस पूरी टर्म के साथ मल्टीप्लाई हो रहा है. Now this is a complex number 1 minus iota. इसका मैग्नीट्यूड क्या है इस टर्म का 1 minus iota का अंडर रूट 2. ठीक है ना अंडर रूट 2. So this can also be written as under root 2 over 2 and some phase, and this phase is some number, okay, anything जो भी माइनस पाई बाई 4, लेकिन एक फेज है. ठीक है? इसको साइन now look at this term. This term is exactly the same as the quantum state here. And some phase of unit magnitude which is prepended with the entire state. ठीक है? Any phase which has unit magnitude with the entire phase does not matter, is irrelevant. ठीक है? This the property of quantum mechanics. This is called a global phase. This is irrelevant. You can ignore it. Now this quantum state is in fact the state here. So you started off by this point. At this point, your state vector lied along the x-axis. You had a magnetic field that is pointing along the z-axis. And if you wait for a particular amount of time, that time is given by omega naught equals pi by 2. Then what is happening? The state vector is precessing, and after this interval of time you land up here, the state alpha plus iota beta under root 2, and if you wait for half the time you will end up here. If you wait for double the time you will end up at this point, which is alpha minus beta under root 2. Okay, so this is how time is progressing. As time is progressing, the quantum state vector, which was lying along the x-axis, is now precessing with a certain frequency, and that frequency is omega naught, the LUMS frequency. So what we've done is that we have created an initial state which was pointing along the x-axis. We placed it inside a magnetic field. And we saw that the state vector was evolving with time in such a way that it precesses with the frequency omega naught. अब इसी expression में omega naught t को pi रख के देखें, you will come here. 3 pi by 4 रख रहे, you will come here. You can take any arbitrary value. you will be moving along the equatorial plane. So previously in the first lecture, we looked at the Bloch equation and saw that the precession of the magnetization takes place with the LUMS frequency. Now we have taken a purely quantum mechanical approach. We have written a quantum state and a Hamiltonian and looked at the evolution of the state under the action of the Hamiltonian and found that exactly the same behavior is observed. Precession with the frequency omega naught in the equatorial plane. ठीक है, ये हमने बात देखी. अब देखो एक क्वेश्चन हमारे ज़हन में आता है कि this is not, how do we achieve this state in the first place? Because initially our state is along IZ. Initially our state is along IZ. ठीक है? So how do we achieve this state? So let's look at another situation, at our second example. अभी हम डेंसिटी मैट्रिक्स की अप्रोच देख नहीं रहे, अभी हम सिर्फ देख रहे हैं क्वांटम स्टेट वेक्टर की अप्रोच. ठीक है, हैमिल्टोनियन के एक्शन के अंदर क्या होता है. नाउ सपोज वी लुक, आवर इनिशियल स्टेट इज at time t equals 0 is alpha. This is our initial state. Okay? Corresponding to this point. And this is more likely to be an equilibrium state. Correct? Alright. Now this is our initial state. Suppose our Hamiltonian is, the Hamiltonian is always given by some frequency multiplied by an angular momentum operator. Because the Hamiltonian is energy. You take the eigenvalues of the Hamiltonian, you get the energy. And energy is simply a frequency. Energy is just a frequency, correct? So any Hamiltonian is just some frequency omega and an operator. Let's make our operator Iy. And let's call this frequency omega 1, so that it is distinguished from omega naught. Suppose this is our Hamiltonian. Now how do we achieve this Hamiltonian? Important question. Physical achievement of this Hamiltonian. देखो यहाँ पे हमारा Hamiltonian था omega naught Iz. How do we achieve this? Apply a field along the z direction. Apply a field along the z direction. And how strong should the field be? The field should be this much strong, right? So you adjust the strength of the field B naught such that your LUMS frequency is omega naught. So it is the strength of the field that determines the frequency, correct? According to the LUMS formula. Now in this case, we apply a field along the y direction. So our field now is along the y direction. Let's call it B1. ठीक है? उसमें हमने B naught अप्लाई किया, अब हमने y direction में field अप्लाई की B1 along the y direction. And omega 1 is simply minus the gyromagnetic ratio into B1. ठीक है? अब फर्ज करो ये हमारे पास हैमिल्टोनियन है, फील्ड हमारी along the y axis है. Now we can solve the Schrödinger equation once again. So our state at time t, arbitrary time, is given by exponent minus iota this Hamiltonian omega 1 Iy into time. Now I can forget about h bar. I can forget about writing h bar because there is an h bar in here as well. So I have not cluttered the notation. Okay? So we have to compute this expression. How does the state change with time? Okay? Now the problem is that Iy is this half 0 minus iota 0. How do we calculate the exponent of this operator? ये आपने पढ़ा लीनियर अलजेब्रा पढ़ा, मैं आपको रिमाइंड मैं रिजल्ट बता देता हूँ। एक हमारे पास थ्योरम है छोटा सा, ठीक है, ये अच्छा हो अगर आपको थ्योरम ये याद आ जाए, या आप इस थ्योरम को अपनी रूटीन में डालें तब याद रहे। ये चीज आसान है, कोई इतना मुश्किल नहीं है। अभी तक जो हमने मैथ की कोई मुश्किल तो नहीं है ना, वेरी स्ट्रेट फॉरवर्ड एंड इट्स फिजिकली इंस्पायर्ड मैथमेटिक्स। Alright, so we have to compute this expression. We start off with a state that is here. We apply a magnetic field that is along the y direction. And let's see what happens. So if there's a theorem which states that exponent minus iota some angle beta, some operator A equals cosine of beta identity minus iota sine of beta A. If A square is identity. So this is a theorem. If you have an operator here or a matrix here whose square is identity, you have any angle here, beta, any angle, and an iota, then this is a theorem. You can prove this theorem. I can give you it as a homework. You use the Maclaurin series just to do this. This is given by cosine beta times identity, which is an operator. देखो ये एक ऑपरेटर है, तो ये राइट हैंड साइड में भी ऑपरेटर होना चाहिए, सिर्फ कोसाइन बीटा नहीं लिख सकते। So you have to write cosine beta into identity minus iota sine beta A, provided A square is 1. A is an idempotent matrix. Now if you look at Iy and take the square of this matrix, you get 1 over 4 you multiply these, you get identity. You get 1 over 4 times the identity. ठीक है, इसका मतलब iy स्क्वायर 1 over 4 टाइम्स द आइडेंटिटी है। इसका मतलब ये है कि 2iy का स्क्वायर आइडेंटिटी, ठीक है। अच्छा, everything is so simple, neat, clean, like crystalline water. There is no impurity in it. Very simple mathematics. Everything is consistent. We are getting physical insight of how the spins are precessing in time. This is the real physical principle on which NMR is based. And a chemist should be happy to know this, of how NMR is working, and a physicist should be happy to know that quantum mechanics really works. ठीक है, तो अब ये देखो, अब ये वाली एक्सप्रेशन है psi t एक्सपोनेंट माइनस आयोटा ओमेगा 1 t। अब i y है, लेकिन हमारे पास हमें 2i y चाहिए क्योंकि उसका स्क्वायर आइडेंटिटी है, तो we put a 2i y here and we divide by 2 alpha. ठीक है, now apply the theorem. Theorem ये कहता है cosine omega 1 t over 2 identity acting on alpha minus iota sine omega 1 t over 2 2i y acting on alpha. We apply the theorem. अब इस थ्योरम को देखें, आइडेंटिटी एक्टिंग ऑन अल्फा इज आइडेंटिटी, अब इस चीज को देखते हैं, आई वाई एक्टिंग ऑन अल्फा इज 1 over 2 अल्फा इज दिस this is iota beta, iota over 2, ठीक है? तो this is जहाँ 1 लिख दें, iota बाहर आ जाए, तो iota beta over 2 आ गया ना?
So बीटा के अंदर इंक्लूडेड नहीं था 1 और 2 बीटा के अंदर इंक्लूडेड नहीं था।
नहीं, बीटा जो है वो ये, ठीक है? So अब so this 2 times this will be iota beta, 2 भी है ना यहाँ पे, तो iota square plus now suppose we adjust the time such that omega 1 over t is pi by 2. Then this state, which started off, the initial state, which started off as alpha, after this much time, pi over 2 omega 1, this will become cosine pi over 4, this will become sine pi over 4, 1 over under root. You will get 1 over under root 2 alpha plus beta. So you turn on a magnetic field which is along the y-axis, for a precise amount of time. That time is given by pi over 2 over omega 1. You will end up here. You will come from here down to here. Okay, you are here. You applied a field on the y direction, you come along the x-axis. Okay? If you wait for twice the time, that is, if your omega 1 t was equal to pi, if you put pi here, this term becomes 0. So you started off with alpha, you waited for pi over omega 1, you end up in the state beta. So you start off here, you end up here. You wait longer, you can go back to alpha minus beta. You wait for a time 2 pi, you can come back here. ठीक है सर, 2 pi का इंतजार करके देखते हैं. ओमेगा 1 t equals 2 pi, cosine of pi बन जाएगा ना ये, which is -1. So you get minus alpha plus sine of pi, which is 0. So you started off with alpha. You waited for a time 2 pi over omega 1. You get minus alpha. But what is minus alpha? Minus alpha is some phase. Phase यहाँ pi है ना, एक इसका magnitude 1 है और phase है, ठीक है? So this does not really matter. Okay, so that is why this is a spin half particle. तो क्वांटम मैकेनिक्स एक ऐसी छलनी है ना जिससे फितरत गिरती है और हकीकत बाहर निकल आती है. Everything is so clean and clear, and with simple mathematics, just the Schrödinger equation and a knowledge of the state, you can tell what's going on. So now what happens in an NMR experiment? In an NMR experiment, you are here in a state of equilibrium. Your initial state is here. You apply some field along the y direction. And your spin comes down. If you switch off this field, here, and you turn on the field along the z direction, it will start recessing like this. So the timing of the pulse is okay, I've used the word pulse, but we'll use it later again. Every NMR experiment can be thought of as a rotation on the Bloch sphere. You apply a magnetic field. The direction in which the magnetic field is applied becomes your axis of rotation. And how much do you rotate is determined by the magnetic field or the time. In this case, you apply the field along the y direction. This is your axis of rotation. If you start off state alpha, you rotate about this axis, you will come here. ठीक है ना, इसी तरह रोटेशन होती है ना, ये एक्सिस है, इनिशियल स्टेट ये है, तो दिस इज योर रोटेशन. If you start off here and this is your axis, you will rotate, your state will go here. Okay, we can draw everything on the block sphere. अभी देखो we talked about states, but only quantum states or vectors, state vectors. We haven't yet talked about density matrices. Now suppose this is your block sphere. Suppose your initial state is alpha. You apply a Hamiltonian or a field along the y direction, which means your Hamiltonian is proportional to Iy. Correct? Correct? Your Hamiltonian is proportional to Iy. This becomes your axis of rotation, and the spin precesses, or the spin rotates about this axis of rotation along a curve like this. It goes back. तो उस वक्त तक प्रिसेशन जारी रहेगी जब तक ये फील्ड ऑन है. So there are two parameters. One is the strength of this field, B1. You multiply B1 by gamma. This gives you this frequency omega 1. ठीक है? This frequency is called the nutation frequency. Nutation frequency. Now this nutation frequency, together with the time for which this field remains on, ठीक है? The product of this time, let's call it Tp, where P stands for pulse. The product of this omega 1 and Tp determines the angle of rotation. ठीक है? If this is pi by 2, you end up here. If this is pi, you end up here. This is 3 pi by 2, you end up here. If this is 2 pi, you end up here. If this is pi by 4, you end up here. You can end up anywhere on the block sphere, on this meridian circle. Longitude का जो circle है ना, इस पे कहीं भी अप्लाई कर सकते हैं. अब सिंपली राइट हैंड रूल लगाना है. ये एक्सिस ऑफ रोटेशन है, जिस डायरेक्शन में फील्ड अप्लाई की, वो आपका थंब है. ये इनिशियल स्टेट वेक्टर है और उसको मूव करता है. ठीक है? तो इफ यू स्टॉप हियर, दिस ऑपरेशन इज कॉल्ड अ 90-degree pulse. It's called a 90-degree pulse in NMR. If you stop here, it's called a 180-degree pulse. Here you can transform alpha state to beta state. You stop here, you get alpha plus beta under root 2. Likewise, if you draw another scenario in which this is a block sphere and your axis of rotation is now lying along the x-axis, that is, your field is along the x-axis. So your Hamiltonian is proportional to Ix, omega 1 Ix, and your initial state is alpha. Then this becomes your axis of rotation, and then you apply the right hand rule. This alpha state will precess along this great circle. It will come here, alpha minus iota beta under 2. It will go on if you don't switch off the pulse. ठीक है? So you can apply a pulse along the x-axis or the y-axis. Okay? And this your applied field becomes your axis of rotation. And you can switch off this field and turn on the field along the z direction. ठीक है? फिर precession along the जब z direction में field होगी तो precession axis of rotation आपको z axis बन जाएगा. So if you are here, the state will be precessing like this. But if you are okay, the third example, we'll talk about 4 examples. Suppose your field is along the z axis. It's b naught k. If your initial spin is along alpha, it will not precess because your axis of rotation and your state are parallel. If your initial state is beta, it will not precess. But if you are on the equatorial plane or you tilted from the z-axis, you will start precessing. And that precessional frequency will be given by minus gamma b naught. So this becomes your axis of rotation. If you are initially here, along on this point, alpha plus beta under root 2, you will start precessing like this. So as time progresses, your state vector is precessing. Okay? So if you place your spins in an external magnetic field pointing along the z direction, this is your scenario. If your field is pointing along the y direction, this is your scenario. If it's pointing along the x direction, this is your scenario.
So in NMR, that like when we perform that experiment, right? So you have the hydrogens in a proton. Okay, so this doesn't apply to many proton systems, just one hydrogen proton system, right?
Right. Exactly. So this applies to one proton. If you have a large number of protons and all of them are identical, they're in the same state, this applies to that case as well. But if you have a mixed state, then you cannot talk about these state vectors. You have to talk about the density matrices. और density matrices की evolution हम अगले lecture में देखेंगे, ठीक है? लेकिन वही principles, वही ideas वहाँ भी बिल्कुल लागू हैं उसी तरह. अच्छा, यहाँ तक बात हो गई. अब देखो, तो क्या NMR एक्सपेरिमेंट में हम कभी फील्ड अलोंग z डायरेक्शन ऑन करते हैं, फिर ऑफ कर देते हैं, और फील्ड अलोंग द x डायरेक्शन ऑन कर देते हैं, फिर ऑफ कर देते हैं, फील्ड अलोंग द y डायरेक्शन ऑन करते हैं, ऑफ कर देते हैं, z की डायरेक्शन? क्या NMR एक्सपेरिमेंट में अभी तक तो लग रहा है कि ऐसा ही हो रहा है कि हम z डायरेक्शन की फील्ड है उसको ऑफ किया, x डायरेक्शन की फील्ड ऑन की, प्रिसेशन हुई, यहाँ रुकी, ये फील्ड ऑफ हो गई, फिर z डायरेक्शन की लॉन्ग फील्ड ऑन हुई, प्रिसेशन हुई. लेकिन NMR एक्सपेरिमेंट में ऐसा नहीं हो रहा. दरअसल अभी मैं थोड़ी सी इस बारे में बात करते हैं. असल में म्यूटेशन फ्रीक्वेंसी हम क्यों कहते हैं? असल में NMR एक्सपेरिमेंट में हम थोड़ी सी आज इंस्ट्रूमेंटेशन की बात करेंगे. व्हाट डज एन NMR स्पेक्ट्रोमीटर लुक लाइक, उससे ये बात और क्लियर हो जाएगी. NMR एक्सपेरिमेंट में होता ये है, वहाँ SSC के ब्लैक बोर्ड पे ना और ये चीज जरा क्लियर वाज़े नजर. Let's talk about water. We want to do NMR spectroscopy with water. Now we place this test tube, which has water, inside a strong magnetic field. And that magnetic field is produced by current carrying coil. Produced by current carrying coil, like a solenoid. ठीक है? तो हम यहाँ से view करें, the solenoid करंट यहाँ से आया और सोलेनॉइड में घूम के इधर वापस चला गया। ठीक है? अब हमें फॉर एग्जाम्पल वी वांट टू डू NMR, say with the we want to produce a magnetic field of 3 Tesla, which means a LUMS of frequency of 42 times 3 megahertz. ठीक है, 126 मेगाहर्ट्ज का हमारे पास NMR spectrometer है. Now, in order to produce this field, we need a very large amount of current. But every coil has a resistance. Large current means a higher value of I square R, which means a lot of heating. Heating raises the temperature of the coil. The coil is made up of some material, it has a melting point. Copper has a melting point of say 1300 degrees centigrade. So it melts. So what we want is a resistorless solenoid. For example, we want a superconductor. It's very difficult to make a wire out of a superconducting wire. It's easier to make a superconducting pellet, but it's difficult to make a superconducting wire. That requires a lot of engineering. But it's possible to make wires or tapes of a superconductor. And the superconductor that is normally used is niobium tin or niobium antimonide. So you make wires or tapes out of this and wrap it around. But superconductor remains superconductor only at a certain temperature. So everything has to be fitted in liquid helium. The superconducting coil has to be inside liquid helium. That's why real NMR is so expensive. Liquid helium पाकिस्तान में नहीं, हमें बाहर से लेनी पड़ती है, बहुत महंगी है. नाइट्रोजन अगर 1 लीटर 100 रुपए की, 1 लीटर अगर 10 रुपए की है, तो हीलियम 1 लीटर 10,000 रुपए की है. और आप अफोर्ड नहीं कर सकते बॉयल ऑफ. ठीक है? So this is inside liquid helium. अच्छा, अब ये लिक्विड हीलियम है, ये सिर्फ सुपर कंडक्टिंग कॉइल्स को कूल करे ताकि इसमें से हाई करंट फ्लो करे. एक दफा करंट आप इसमें से गुजार देना, उसके बाद आप लेस्को और वापडा से बेनियाज हो गए, क्यों करंट हमेशा गुजरते ही रहना है. अगर वो लिक्विड हीलियम अपनी जगह है, कोई वेपोराइज नहीं हो रही, वो लीक नहीं हो रही. ठीक है? लेकिन एक बात ये, और सैंपल हमारा रूम टेम्परेचर पे याद रहे. अब ये है 4 केल्विन, ये है 300 केल्विन. लिक्विड हीलियम तो बहुत जल्दी वेपोराइज होना शुरू हो जाएगी अगर 4 केल्विन को रूम टेम्परेचर. तो इसके गिर्द में आप एक और जैकेट डाल देते हैं जिसके अंदर लिक्विड नाइट्रोजन डालते हैं, so that the temperature gradient is reduced. Okay, this is liquid nitrogen. Okay, so that the temperature gradient is reduced. Now this magnetic field produces a field along the z direction. This current produces a field along the z direction. B naught. और ये है वो फील्ड जो डिटरमिन करती है लामा फ्रीक्वेंसी. अब you cannot switch off this field. This field is always on. Switching off this field requires switching off the supercurrent. But switching off the supercurrent means such a large current has to be switched off. According to the Faraday's law, a large flux is generated. Because you're switching off a current, which means rate of change of current will produce a very large flux. It's not easy to do that. ठीक है? अच्छा, तो ये फील्ड हमेशा ऑन है along the z direction. अभी तक जो हमने ब्लॉक्स किए थे, देखो उसमें z डायरेक्शन के लॉन्ग फील्ड को हम ऑफ कर रहे हैं किसी वक्त. अगर हमने एक्सिस ऑफ रोटेशन x एक्सिस या y एक्सिस बनाना है तो हम अज्यूम करें कि z डायरेक्शन के लॉन्ग कोई फील्ड नहीं. लेकिन यहाँ हमें टेक्नोलॉजिकली पता चल रहा है that Z field has to remain on. ठीक है? All right. So this is the static condition. Now what happens is that close to the sample, close. I will show you pictures of NMR spectrometers as well. Ali Daza is trying to build one for us. We don't know what the outcome is going to be, but we hope that something will come out of it. So this is the static field, the background field. Now we have to apply pulses, fields along the x direction or the y direction. Suppose close to this sample, we have another coil. ठीक है? और हम एक्सिस बना लेते हैं, ये z एक्सिस है, ये x एक्सिस है, ये y एक्सिस है. So the field, this solenoid is along the z axis. Okay? And this solenoid is an inductor. Solenoid एक इंडक्टर होता है ना. अच्छा. अब अगर आपको याद हो इलेक्ट्रोमैग्नेटिज्म के कोर्स में, तो कोई भी इंडक्टर है L, ठीक है? अगर उसके पैरेलल में एक कैपेसिटर लगा दें तो एक LC सर्किट बन जाता है और उसकी एक रेजोनेंस फ्रीक्वेंसी होती है. ठीक है? And that resonance frequency F is given by 1/2 pi under root LC. अब ये एक इंडक्टर है, ये कैपेसिटर है जो वेरिएबल कैपेसिटेंस है. बिल फर्ज B नॉट आपने फील्ड अप्लाई की 3 टेस्ला और फिर आपको पता चल गया लाम ऑफ फ्रीक्वेंसी इज 126 मेगाहर्ट्ज. Now you tune this coil, you have a fixed L, you tune the capacitance such that the frequency turns out to be the same as the Lamb frequency. ठीक है? और इस चीज को आपने एक फंक्शन जनरेटर के साथ कनेक्ट कर दिया जो ट्यूनेबल है. इसको आपने 126 मेगाहर्ट्ज दिए. जब ये कॉइल रेजोनेंस में आई तो इसके अंदर से करंट गुजरा. रेजोनेंस की वजह से वो करंट बहुत ज्यादा है, एक मैग्नेटिक फील्ड प्रोड्यूस हुई उस करंट, इस सोलेनॉइड की वजह से भी एक मैग्नेटिक फील्ड प्रोड्यूस हो गया और उसकी डायरेक्शन along x होगी. तो you have a magnetic field B1 along the x direction. Will this B1 be larger or B0? B0 will be much larger. B0 will be much larger. So if this frequency is in megahertz, because frequency is gamma times B, this frequency is in megahertz, this frequency omega 1 is expected to be much smaller than the Lamb frequency. क्योंकि ये जो omega 1 है ना माइनस gamma B1 है, तो चूंकि ये फील्ड बहुत कम है, ये सुपर कंडक्टिंग कॉइल नहीं है, ये नॉर्मल रूम टेम्परेचर कॉइल है, तो इसमें से जो फील्ड प्रोड्यूसर बहुत कम है. तो जो ये फ्रीक्वेंसी है ना, इसे म्यूटेशन फ्रीक्वेंसी कहते हैं, ये बहुत कम है. अगर लाम फ्रीक्वेंसी मेगाहर्ट्ज में है तो किलोहर्ट्ज में है. Now suppose, so this is the scenario. ठीक है? This is the basic schematic of the NMR spectrometer. Now let's connect this with our block sphere picture. And let's understand what is going on. This is our block sphere. Initially, our spin is along the state alpha. A field, okay. along V नॉट है, तो हमेशा से ऑन है ना, हमेशा ऑन है, अजलता अबद, क्योंकि सुपर कंडक्टर है, जब तक लिक्विड हीलियम बरकरार है उसने ऑन ही रहना है, कोई खर्चा भी नहीं बिजली का इसमें, ठीक है ना। ये फील्ड इसलिए ये ऑन है हमेशा, बहुत स्ट्रॉन्ग है फील्ड। अच्छा, लेकिन अब आप ये करते हैं कि B1 के अलॉन्ग स्पिन्स हैं इस डायरेक्शन में, along alpha, they're not precessing because the axis of rotation, ये फील्ड अभी ऑफ है, B1 फील्ड, the axis of rotation is the same as the spin vector, direction of spin vector. Now at a certain point in time, let's call it T1, you switch on the field B1, you switch on the field B1, okay. Now this field is a sinusoidal field. Sinusoidal field means it has a profile like this. It has a certain amplitude B1 max. This is minus B1 max. It's a sinusoidal field. ठीक है, इस सोलेनॉइड में से ज़रा डीसी पे तो काम ही ना करेगा, ये एलसी सर्किट है, डीसी पे इसने काम नहीं करना, इसने एसी पे काम करना है, you have to drive it at a certain frequency, ठीक है, you have to drive it at a certain frequency, because the Lama frequency is 126 megahertz, you have to drive it such that the driving frequency is also 126 megahertz, so that there is resonance between your applied radiation and this Lama frequency of the springs. That's why it's called nuclear magnetic resonance. So you apply a sinusoidal field. Sinusoidal field का मतलब कि टाइम में बढ़ रही और कम हो रही है, बढ़ रही और कम हो रही है। अगर हम ऊपर से देखें, ये अगर x डायरेक्शन है ना, इसका क्या मतलब है? इसका मतलब ये है कि if you look in the x direction, ऊपर से देख रहे हैं, ये x है, ये y है, ठीक है? फील्ड इस टाइम पर t1 पे अपनी मैक्सिमम स्ट्रेंथ पे है, इस टाइम पे, फिर वो कम हो रही है, यानी द फील्ड इज डिक्रीजिंग विद टाइम। इस पॉइंट पे फील्ड जीरो होगी टाइम में, फिर फील्ड रिवर्स डायरेक्शन में इंक्रीज होगी, और फिर अपना तो ऊपर से अगर आप देखें ना ज्योमेट्री को, यहां से ये आंख है, ये कोई बसीरत वाली आंख ऊपर से देख रही है। अब वो एक्स डायरेक्शन में फील्ड है, साइनसॉइडल है, बढ़ रही है कम हो रही है, बढ़ रही है कम हो रही है, ऑपोजिट डायरेक्शन में जा रही है, ठीक है, तो इस तरह फील्ड वेरी हो रही है, ठीक है, ये मतलब है इसका, ओके। अब आपने एक टाइम पर इस B1 फील्ड को ऑन किया और एक टाइम पर इस फील्ड को ऑफ कर दिया T2 पर, और फिर ये ऑफ ही रहेगी। अब ऐसी हालत में क्या हो रहा है? अब ये जो B1 मैक्सिमम फील्ड है, इसकी एम्पलीट्यूड बहुत कम है ना इस फील्ड से, तो इस ड्यूरेशन में ये फील्ड भी ऑन है, ये फील्ड भी ऑन है। तो आप देखें टाइम t0 तक ये स्टेट वेक्टर यहीं पे रहा, the NMR spin remained along the z-axis. When this time approaches at t1, it starts moving down because the axis, it starts moving down, ठीक है? But at the same time, because of this field, it is precessing, so it starts coming down in a spiral. Starts coming down in a spiral. ठीक है, इस तरह। And this horizontal precession is much faster than the precession which it comes down. In other words, there is an effective axis of rotation which is not along the x-axis It's neither along the z-axis but slightly tilted from the z-axis. So this kind of motion is called nutation.
The given of the alpha beta in setting.
And if you adjust the time t2 minus t1, let's call it tp. tp is the time of the pulse. If you adjust this time such that omega 1 tp is pi by 2, you will end up here. So this kind of pulse is called a 90-degree pulse. And this is the simplest NMR experiment you can do. You apply a pulse along the x or the y axis for precise amount of time which is given by this expression. Now there is only one solenoid along the x. How do you apply a pulse along the y? Using this solenoid. You cannot change the coil. You're not allowed to change the coil. So you change the phase of this. Instead of starting here, you start off here. Okay? Instead of making a cosine, make it a sine, because sine and cosine are different by 90 degrees. So you apply a sinusoidal B1 field for a precise amount of time, and that time controls whether you have a 90-degree pulse, a 180-degree pulse, or a 45-degree pulse. And this is called a pulse. So the simplest NMR experiment is your B0 field is always on. You apply a 90-degree pulse along the x or the y axis. You get onto the equatorial plane, and then the spins start precessing. And when the spins start precessing, they are moving in the equatorial plane. When they are moving in the equatorial plane, we know that whenever we have a spin precessing in the equatorial plane, corresponding to the spin, there is a magnetization. And that magnetization will produce a change in flux in the coil, and that can be detected. And so what do you require? You require something. This function generator is not an ordinary function generator. This function generator should be able to apply a phase as well. Okay? So the function generator should in fact have phase capabilities, so that your axis of rotation can be along the x-axis, it can be along the y-axis. In fact, it can be at any phase. So your axis of rotation is ix cosine phi plus iy sine phi. So this is not an ordinary function generator that is available in the physics lab. This is a function generator that can apply a known phase. और इस फ्रीक्वेंसी पे काम करें फेज इलेक्ट्रिकल इंजीनियर भाइयों से पूछें, जो तादाद में इतने ज्यादा उनसे पूछें, कहेंगे यार ये आसान है, कर सकते हैं, नहीं हो ना बात, लेकिन कहेंगे आसान है, फेज हमारे कंट्रोल में. ठीक है? तो फेज प्रोड्यूस करना बहुत जरूरी है. और फिर आप देखो कि जब आपने टिल्ट कर दिया along the x in the xy plane अपने स्पिन को, अब वो प्रोसेस कर रही है, वो किस फ्रीक्वेंसी से प्रोसेस कर रही है? ओमेगा नॉट से. अब रेट ऑफ चेंज ऑफ फ्लक्स भी ओमेगा नॉट की एक फ्रीक्वेंसी होगा. अब इसी कॉइल को पहले हम ट्रांसमीटर के तौर पे यूज कर रहे हैं, इसमें ट्रांसमिट कर रहे हैं रेडिएशन. ये पल्स, we are throwing this pulse onto the spins. Now we change gears. When we change gears, we are using the same coil as a receiver. अब उसी कॉइल के ऊपर आपको एक सिग्नल मिल रहा है of the frequency omega naught. Axis of rotation is along the z-axis because the z-axis is always on. तो इसी एक्सिस पर एक्सपेरिमेंट कैसे काम करता है? आपने ये पल्स अप्लाई की, पल्स ऑफ हो गई. Suppose this is a 90-degree pulse. This achieves the spins to come onto the x point. अब ये पल्स ऑफ कर दी. अब ये फील्ड तो ऑन है, तो अब उसके तहत spins will start precessing the frequency omega naught. अब यहाँ पे क्या करें? यहाँ पे इस कॉइल का रोल बदल दें. यहाँ पे the coil is acting as a transmitter. Now the coil is receiving signal at the same frequency omega naught. It's acting as a receiver. So here what you do, this signal goes inside an ADC. अब सिग्नल ट्रैफिक को डाइवर्ट कर रही है. सिग्नल पहले यहाँ जा रहा था, अब द सिग्नल comes to the reception side. The signal comes to the reception side. यहाँ पे कोई आपके पास स्विच होगा जो कंट्रोल कर सकता है कि ट्रांसमीटर के तौर पे एक्ट करना है या रिसीवर के तौर पे. कंप्यूटर कंट्रोल है. जब पल्स ऑफ हुई तो it starts acting as a receiver. Now this signal comes into an ADC. ADC is analog to digital converter. ये इस सिग्नल को ना डिजिटाइज कर देता है. तो आपके पास जो सिग्नल रिसीव होगा ना वो सैंपल्स होंगे कंप्यूटर में, ठीक है, उसी फ्रीक्वेंसी ओमेगा नॉट के. और ये स्पिन्स के कासिद हैं, स्पिन्स के पैगामबर हैं. स्पिन्स के बारे में बता रही हूँ कि क्या लैम्डा फ्रीक्वेंसी है. उसका फिर आप फोरियर ट्रांसफॉर्म लेके आपके पास एक स्पेक्ट्रम आ जाएगा. अब स्पेक्ट्रम के बारे में हम अगले लेक्चर में बात करेंगे. So an NMR has a magnet and has a spectrometer and a coil, one coil which acts as a transmitter and receiver at the same time. It's called a transceiver. So this is the basic overview of NMR. Now look how we have connected basic quantum mechanics, the Schrödinger equation, quantum mechanics 101, basic thing you learn with something that electrical engineers have to deal with. Or they make visible signal. ठीक है, thank you very much.